We're going to talk about cracking long-chain hydrocarbons in this video, specifically cracking long-chain alkanes. Okay, alkanes are found in crude oil. Okay, alkanes are found in crude oil. So crude oil is a mixture of alkanes of different chain length. There's some very short molecules, like molecule A here, and there are some longer molecules, like molecule B. In fact, there are some much longer molecules. I just didn't have enough space on the paper to draw one out. First question says, look at molecule A and B and decide for which you think humans have the higher demand. Okay, the answer is A. Why? Smaller chains. So when I say chains, I mean the number of carbons on the backbone. This is a small carbon chain, this is a long carbon chain. So smaller chains are more flammable. Okay, and what you need to remember here is, as humans, we mainly burn fossil fuels or crude oil, alkanes. We mainly burn them as fuels. Okay, crude oil is mainly used as a fuel. Mainly used as a fuel. Petrol, for example, that fuels cars, short chain. Gas that's used in central heating systems in the home is a very short chain. Shorter chains are better fuels. Crude oil is mainly used as a fuel. Shorter chains are better fuels. So that means we've got some long chain molecules that aren't really very useful because they're longer, they're not very flammable. If they do burn, they burn with a smoky flame. So what chemists started saying is that, well, these are useful and these aren't. What can we do to this to make it more like that? And the answer is we need to cut the chain. So we could call this cutting long chain hydrocarbons, but actually cracking. If we crack the molecule, we break it apart. I mean, it's the same thing. So cracking is breaking the molecule apart. Think about it. If we asked 20 of you, 20 students, to link arms in a straight line and spin around progressively faster, what do you think would happen to people on the end of the line? So instead of carbons, if there's 20 people all linked arms and we ask you to move around slowly, you could probably move around like that, couldn't you? It would be quite cumbersome and quite difficult, but you could probably do it. But if we ask you to run around like that, and it wouldn't be long before a couple of people broke off the end. And that's how we crack long chain hydrocarbons. We don't ask the molecule to run around, but we do make it move around faster. How do we make a molecule move around faster? We heat it up. Okay, so let's put some answers down here. What would happen to the end line? A couple of students, we could say would fall off, but let's use the term crack. Would crack off, basically break off the chain. So we'd end up with a shorter chain. Okay. If we had a long chain hydrocarbon like molecule B, how could we make it move around more quickly? Answer, heat it up. Now you've got to heat it, but without oxygen, because of course if there's oxygen, you heat it, it burns. Okay, this process is called cracking. So let's have a look. So complete the equation. Assume one product has the formula C8H18. So this is the reactant, our long chain. We're going to heat it up, and one of the products is going to be C8H18. That means the other product has to contain 2 carbons. If we start with 10 carbons here, and there's 8 on this side, there has to be 2 left over. Likewise, if there's 18 hydrogens here, and we started with 22, 22 minus 18 is 4, C2H4. So when we crack that compound, we heat it up, it wobbles apart, it wobbles into 2 smaller molecules, one a little bit shorter and one much shorter. Draw the structure of the smaller product, so it's C2H4. And that's how we would have drawn it up until now. Okay, problem. What's the problem with that? Well, carbon should form, sorry, you can't see it now, can you see it? Can you see this now? It says draw the structure of the smaller product. So we've got C2H4, we've drawn C2, and we put 4 hydrogens around it, spread them out. What's the problem? Well, carbon should form 4 bonds. Okay, if we look at it here, it's forming 1, 2, 3. That's a problem. Now come back up to the top here. These carbons all form 4 bonds. 1, 2, 3, 4. Carbon needs to form 4 bonds in these hydrocarbons. Problem, carbon is only forming 3 bonds. Solution, well, molecule still contains that number of carbons, that number of hydrogens. We can't change that. But we'd need to give the carbon an extra bond. Well, that's put a second bond between the two carbons. Okay, and what we have here is a carbon to carbon, carbon to carbon, double bond. So this is we now get a different homologous series. This homologous series is called the alkenes. Alkenes. Previously, these were alkanes. That's an alkane, and they have single carbon-carbon bonds with an A there. These down here now are alkenes with an E. Be careful with your E and the A. Okay, and that one was 2 carbons. That's going to be ethene. If you are a double scientist, you don't need to know that's called ethene. If you're a triple scientist, a single chemist, you need to know that's called ethene. Okay, so how do we do this? How do we do this? Well, we could use this apparatus here, and if you're in school, we'll do this as a class practical. So basically, we're using paraffin. There's our long chain alkane. So paraffin is a viscous liquid, or even a solid if it's a candle, I suppose. It's a hydrocarbon. It's made of carbon and hydrogen only. It's an alkane. That is the long chain alkane. It's not a great fuel. Yes, we can burn it as candles, but you can't put candles in a car petrol tank. The purpose of the heat, that is to crack the alkane. It wobbles the alkane apart. The crushed brick, that's a catalyst. Basically, brick is porous. It's got lots of holes in it. You could use broken pottery as well. Anything with holes in it. Basically, as the hydrocarbon heats up, it becomes a gas, and it sits in those holes in the hot brick and just wobbles apart in there. Okay, so it speeds up the reaction. Catalyst speeds up the reaction. Okay, now there's a couple of different catalysts, and if you see it in an exam, just be aware there'll be a catalyst there. Gas X. Gas X now, come back to this side. Remember, the shorter the chain, the more like the lower the boiling point. So gas X is going to be this molecule here, okay? C8H18, that's more likely to be a liquid at room temperature. This one here certainly be a gas at room temperature. The shorter the chain, the lower the boiling point. Gas X is the alkene, Okay, if you're doing full chemistry, you need to be able to test gas X. Okay, and show it's an alkene and not an alkane. And the way they do that is they use bromine water, but we'll go back through this in the triple work later on. Bromine water, and it goes colourless or decolorizes. Okay, don't say goes clear is wrong. Goes colourless in an alkene. It stays brown, stays orange, brown in the alkane. Goes colourless in the alkene. So that's an important one if you're a triple scientist. Right, back to double and triple. Give 2 reasons why cracking is an important industrial process. The first one makes shorter chain alkanes. Okay, so if we shorten the chain, we make better fuels. So we can turn hydrocarbons, like this one C10H22, that's our long chain alkane. Long chain alkane. Can't put that in a car petrol tank. Okay? Okay, that's not a good fuel. Not a good fuel. Okay, but by cracking it, we take the chain that was 10 carbons long and make it 8 carbons long, and this is now a shorter chain alkane. Shorter chain alkane. And that is a better fuel. Shorter the chain, more flammable, the better the fuel. So that's the first thing. So suddenly we've got much more petrol, and we've got a great demand for petrol for cars. So the first thing, makes shorter chain alkanes, that makes better fuels. The second advantage, second reason it's an important industrial process, is it makes alkenes, this second homologous series with the carbon-to-carbon double bond. Alkenes are not in crude oil. The way we get alkenes is by cracking long chain alkanes. Now in year 10, if you remember, okay, we looked at polymers, okay, as long carbon chains and how they were formed. Okay, just to remind you, remind everybody, this is in the triple science unit for Edexcel as well. You take all these alkenes, there's our alkene, and if we heat that and pressurize it, we can make that double bond spring open, and we end up with these hugely long chains. This is in the year 10 book, just to remind you. Okay, so we end up with something with about 30 to 40,000 carbon chains, and that of course is a polymer. Okay, and a polymer is plastic. Okay, so how do we get plastics? Well, to make plastics, we need these alkenes. So it makes alkenes, and alkenes are the raw material. They're not plastic, they're the raw material for making plastic. Making plastic. And that is polymerization. So, and we did that in year 10, polymerization. So that is part of the topic 1 that we did in year 10. Okay, year 10, topic 1, if you want to remind yourselves of that. It's also in the triple unit. I don't think it'll be tested too much in the double science because it's a whole triple unit as well, but we did talk about it there. Complete this cracking equation, draw the structure of the alkene. So again, this here is double, this here is probably triple, but let's go through it. Okay, so C11 on the left, so on the right we've got C8, so there's 3 more carbons left over. 24 hydrogens on the left, 18 on the right, so there's 6 left over, so 6 and 18 makes 24. And the alkene structure has 1 double bond, so this is the alkene with 3 carbons now. Remember, carbon forms 4 bonds, so if it's 1 there, it's got 1, 2, 3 more. On those extra bonds, we put hydrogen. This carbon here has got 1, 2, 3 bonds already, so it only needs 1 more. This carbon here has got 2 bonds, so it needs 2 more. You can draw them where you want, I suppose, but there you go. There's propene.